In the last video, we learned how to find volumes of solids revolved about either the x or the y axis, and in that video none of the solids had holes in them. So in this video we're going to continue that discussion of how to find the volume of a solid that has been created by revolving a region about either the x-axis or the y-axis, but this time there is a hole in that solid. So we start with this warm-up. Let's take a look at what we have here. We have basically a washer or a donut or a circle within a circle, and the question or statement says, give a formula for the area of the shaded region if the inner radius is r of x. So the inner radius would be the distance from the center to the circle. So that little segment right there, blue, is r of x. And then it says that the outer radius, the distance from the center of the circle to the outer edge, so red, is big R of x. Well, if we want to find the area of the shaded region or the black shaded region, we know that the area of a circle is pi r squared. In this case, we're going to take the big circle, which is the outermost circle. We're going to find the area of that, so that would be pi big R of x squared, and then we're going to subtract the small circle, which has a blue radius, and when we subtract that and find the area of that circle, we have pi little r of x squared, and that would leave me the area of the shaded region. And that's basically the principle that we're going to use to find the area of to find the volume of a solid that has a hole in it. So let's take a look at a couple of examples. Most of the premise is the same as it was in the last lesson. So, number one, find the volume of the solid formed when the region enclosed by the following curves is revolved about the x-axis. Since we're revolving about the x-axis, we will be in terms of x. So I'm going to graph this region. The first thing I notice is that this function or this relationship is solved for x and not for y. So I'm going to get y by itself, and that will give me square both sides. That'll give me x squared. I'm going to add 1 to both sides, and I get y is equal to x squared plus 1. Now remember that this indicates that it wants the positive side of that parabola. I have x equal to 0. And I have y equal to 5. So y equal to x squared plus 1. So there's 1. Again, wanting the right-hand side because it doesn't say plus or minus, it just says the positive side. X equal to 0 is the y-axis, so there's another boundary. And then y equal to 5, we'll call that right here, y equal to 5. So this is the region that we're going to revolve about the x-axis. And when we revolve that region about the x-axis, I'll kind of give you a little idea of what that would look like. Again, my artist skills are not that great. But it would reflect over the x-axis, so we would have something that looks kind of like this. And so this is the region that gets reflected. And the circular motion would give me something like this. So there's the hole. And as you travel throughout the circle, the object, the hole gets bigger and bigger. So the size of the hole is changing. Alright, so we want to collect all the area, but again, we have to get rid of the hole. So when we put in a radius, the radius of the outer circle is the distance from the axis of revolution to the outer curve. So big R, if you think about what we had before on the other page, we had the big circle and then we had the little circle. What we're actually finding right now is the radius of the outer circle. So then we have to also represent the radius of the inside circle, which is really the radius of the hole. The radius of the inside is the distance from the axis of revolution to the inside curve. So you can see that there's definitely there is space in between the region that is being revolved and the x-axis. And that space between the axis of revolution and what's being revolved creates the hole. So if you look over here at the circle that I created, the radius that we just found is the distance from the axis of revolution to the inside circle. So we have a big R and a little r, and in this case, my big radius, the radius of my big circle, is in red. So r of x, as we stated before, is the distance from the x-axis to the outer curve. Now the outer curve in this case is y equal to 5, so the outer radius is always 5 units long, because the outer curve is that horizontal line y equal to 5. Little r of x is the distance from the axis of revolution to the inside curve, which is going to be x squared plus 1. So when we collect the area, we're going to use that principle that we had before. Remember, we said the area, if we want the area of this region right here, it's going to be pi big R squared minus pi little r squared. So we're going to use the exact same principle. Just like before, we can pull the pi out as a coefficient, since both areas will have a pi in it. We're going to collect the area starting at, remember we're in terms of x, so we're going to start at 0, and then we're going to stop collecting the area right here. So we need to figure out where that parabola is intersecting the line y equal to 5. So I have x squared plus 1 equal to 5. So x squared is equal to 4. So x is equal to plus or minus 2, but this is on the right side of the axis, so the upper bound is going to be an x value of 2. So this value is 2. So up here this point is 2, 5. Alright, so now we need big R of x. So big R, remember, was 5. So we have big R squared minus, so now we're getting rid of the whole. Little r of x is x squared plus 1, x squared plus 1 squared dx. And again, this is big R of x squared, and then we have minus little r of x squared. That's what's happening here. So when we find the antiderivative of that, I'm running out of space here, but all we're going to do is make this equal to pi. We'll square the 5 and get 25. We're going to square the inside of that, so I'll get x to the 4th plus 2x squared plus 1 dx. I'm going to combine the like terms, find the antiderivative, and evaluate that from 0 to 2. The main part right now that I want to demonstrate and show you is how to set up the integral that will accumulate the volume of that solid. Again, to get rid of the whole, it's big R of x, the big radius, minus the little radius. Alright, let's take a look at the next one. Find the volume of the solid when the region enclosed by the following curve is revolved again around the x-axis. So we are in terms of x. Alright, so let's see what we have here. Y equal to the square root of x looks something like that. Y equal to x squared, I'm going to exaggerate it a little bit, looks something like that. Yeah, of course, y equal to x squared goes on the other side, but I'm looking for I'm going to revolve the region that's enclosed by those two curves. So this is the square root of x, and this is x squared. I'm going to revolve that around the x-axis. Again, I'll show you what the reflection would look like. You don't have to draw this. The reflection would look something like this. And then the circular region, you can see that there's a hole all the way until you get to the point of intersection at the origin. It looks kind of like a flower or something. So here we go. If we want to find the volume, we know that we're in terms of x, so we're going to have a pi on the outside. We're going to have a lower bound and an upper bound. We're going to have a big R squared minus a little r squared, and we are in terms of x. So this will be big R of x, and this will be little r of x. So we first of all have to find the outer radius. The outer radius is big R of x, and that is the distance from the axis of revolution to the outer curve. The axis of revolution is the x-axis, and in this case the outer curve is the square root of x, so the square root of x determines the length of the outer radius. The inner radius, little r of x, is the distance from the axis of revolution to the inside curve. So from the axis of revolution, the x-axis, to the inside curve, and the inside curve in this case is x squared. So x squared is determining the length of the inside radius. So little r of x, big R of x is the square root of x. Little r of x is x squared. So when and we're going to evaluate that from 0 is the first point of intersection. Second point of intersection, I'm going to set those two curves equal to each other, so I'll have square root of x equal to x squared. I'll square both sides, and I'll get x equal to x to the fourth, and then I'll move everything to one side. X to the fourth minus x equals 0. Factor out an x. I'm going to move that up, and I'll have x times x cubed minus 1 equals 0. So I get x equal to 0 and x equal to 1. So I'm going to go from 0 to 1. I'll take it one more step. So that would be pi, the integral from 0 to 1 of x minus x to the fourth. Well, I'll take it even one more step. That would be pi x squared over 2 minus x to the fifth over 5. Evaluated from 0 to 1, and you can do the arithmetic. Again, the main idea, we're trying to get rid of the whole, so we have to take the area of the outer circle minus the area of the inner circle. All right, let's take a look at one more maybe, and let's do one in terms of y. And this one is in terms of y. We're finding the volume of the solid formed when the region enclosed is revolved about the y-axis. So this time we are in terms of y. Now this equation is not solved for y, so we're going to solve it for y by taking the ln of both sides. So I get the ln of x is equal to y times the ln of e. I just use the log property to bring my exponent down. The ln of e, of course, is 1, so I have y equal to the ln of x. So when I graph this, y equal ln of x is the inverse of e to the x. It goes through the point 1, 0, and it has a vertical asymptote of the x-axis. So it looks something like that. The line x took care of that. The line x equal to 5 is a vertical line. I'm just randomly sticking a 5 up there to get a visual idea. And then y equals 0 is the x-axis. So the region that we're revolving is this region right here. And we're revolving it around the y-axis. So the reflection, and I'm not going to have room on the board, but the reflection would look something like that. It would keep going over here. I'm going to make it smaller. This would be -5, and so the whole is here and here. So you definitely can see that there's going to be a hole. And I'm going to highlight, we're revolving it around the y-axis. So this time we're going to have, just like before, we're going to have an outer radius and an inner radius. We'll have a big R of y, and we'll have a little r of y. Big R of y is the distance from the axis of revolution to the outer radius, which in this case is always 5. Makes it kind of easy. The inner radius is the distance from the axis of revolution to the inside curve. Now be careful, because we're in terms of y, the distance from the y-axis to the inside curve is going to be this function, but it's going to be in terms of y. So that distance is represented as e to the y, not ln of x. We want the function or the problem in terms of y. So our setup is pi on the outside. We're going to go from, we'll figure that out in a second. We're going to have big R of y squared minus little r of y squared dy. So again, That's big R of y, little r of y. And in our problem, big R of y was 5. Little r of y is e to the y. We're collecting the area in terms of y, so the lower bound, we're going to start the collection at 0, and then the upper bound, we need the y value where those two curves intersect. So I know that the x value is 5. I can substitute it in here, and I know that y is equal to the ln of 5. So we're going to collect area from 0 to the ln of 5. Cleaning that up a little bit will give me pi from 0 to the ln of 5 of 25, that's 5 squared, minus e to the 2y dy. When I find the antiderivative of that, I'll get pi 25y minus, now again, yesterday we did a problem like this. The e to the 2y technically needs a u substitution, and you can come down here if you want to and do u equal to 2y, du is equal to 2 dy, and we're going to get rid of the 2, divided on both sides. So we would have half the integral of e to the u du, which is e to the u over 2. So that would give me over here 1/2 e to the 2y evaluated from 0 to the ln of 5. And that would be pi, looks like I'm going to run out of room here. Let's see how much I can do here. Pi multiplied by, substituting ln of 5, so that would be 25 ln of 5 minus 1/2 e to ln of 5 minus, substituting in 0, 25 times 0 is 0, and e to the 0 is 1, and 1 times 1/2 is 1/2. I'll try to finish this problem up, space permitting, get rid of some of this stuff down here. So that would be pi times 25 ln of 5. Now this right here is the same thing as e to the ln of 25, because we can take the power back on to 5. So e and ln undo each other, and I have half of 25, so I'm going to just write that as minus 25 halves minus negative 1/2 is equal to pi times 25 ln of 5, and then I have a negative 25 halves plus 1/2, which would give me negative 24 halves, which is negative 12, and that works as an answer. So in review, if you have your packet in your notes, this is a kind of a quick review of how to find the volume of a solid with a hole in it. Hopefully you will find this video helpful. If you need more help, come and see me.